Hi friends, good morning. So we are into second week or second module of risk conscious operations management of complex engineering system. Now this is the second lecture on dependability engineering, and in this lecture we will cover introduction part, because unless until you know the background, probably it will be difficult to get the concept right. Because risk engineering is a very important subject, because when we develop the mega system. So what I mean here by complex engineering system means, though in my previous presentations I have explained it, but then every presentation we must keep it in mind what the subject or the application area that we are dealing in. Complex engineering system is synonymous to something like mega system, or where humans are manning the system to ensure the operability and safety. And these systems are, because there are so many interconnection and dependability on resources, their smooth operation should be ensured. And then if there is any element of safety issues, that must be attended to. And in these systems there are prior provisions they have been made, so that the safety can be ensured by reducing risk in a perpetual manner, such that the system deliverables are ensured. As I mentioned, I'll introduce you to the subject, that is dependability engineering, and this is basically second week of this course. I am Professor Prabhakar V. Vardhe, Director of a startup engineering risk assessment and management, ERMC, and then this is an NPTEL course on risk-based engineering or risk conscious operation management. Yeah, of course, it is one of the spin-off of risk-based engineering. So let us start. So sort of introduction I have already given you. By calling risk conscious operation management, that means risk should be and in perpetuity consciously should form up operation management, whether it is documentation, whether it is design of the plant, whether it is human factor training or control room manning. Everywhere this element should be consciously ensured, so that any deviation or engineering risk scenario can be handled. And then background and interface. Well, this reliability engineering subject has evolved over almost like 40-50 years, and traditionally it was reliability, then reliability, availability, maintainability, they joined. So together as a package it used to be called as RAMS, that is reliability, availability, maintainability and safety. But here you see here RAMS S, which should be an because safety is an overriding factor. So psychologically also anything coming at the end which is an overriding factor should be thought more seriously actually. So when we say that safety should be primary or overriding factor, then risk becomes, because risk being a mathematical component of engineering, then risk reduction should come. So that means what we are talking about is a risk-based approach, which should answer not only risk-related or safety-related issues, but that should answer even reliability-related, availability-related. So the probabilistic risk assessment is a tool where whether it captures these type of concepts. Again, as far as the designs are concerned or operations are concerned, the traditional approach was deterministic in nature. it was initiated in 50s, and then it did really well. But then improvements as the system become more complex. In those days digital technology was not there, softwares were not there. Now we have more complex thing. Ergonomics has moved to something like, in control room we have digital technology, advisory tools, and many digital system they are supporting. Of course, in certain industry, having digital system having their way in control room is thought out, and regulators give permission only when they ensure that there are adequate redundant provisions to ensure safety. So now we have reliability engineering, availability engineering, maintainability engineering, and risk engineering, and we'll see how we shape this all the areas. And in all this technology, whether reliability, availability, maintainability, there are some special area like common cause failure, human factor, and so that I think in one slide we'll cover just to complete the topic. So let us see what we are talking about the systems. Actually, in a generic word, these complex engineering systems, they can be even related to asset and asset management. And when we talk about the asset management, means it's a design, it's operation, it's maintenance, all. So the area generally, just for understanding, it covers industrial system, infrastructural system, road transport system, aviation space system, financial sector system, defense system, and mining system. There are many. Few I have listed just to get a feel of it, what we are talking about actually. So then evolution of expected performance metrics. So as I mentioned in my previous slide, that as the ramps or reliability paradigm got matured, then many things joined, and now like for example, to begin with, security was not there. Now we have a security is one of the important, so we call security safety. Okay, so these kind of new terms they got added up, and then finally the world is moving from traditional reliability or deterministic approach to risk based or risk informed approach, and that is true even for dependability. Why we have chosen this word dependability? Because operations is dependent, smooth operation I would say depends on many factors. Many factors, it might include resources, that means there should be logistics that should be available, human resource, one of the important thing, and then document that should be available. So it is depending on many factors for its smooth operation, and all these operations should have what metrics? They should be reliable. They should be available when demanded. Even it could be engineering system also. So that is how this dependability engineering is the focus of this week, and how we ensure that on documents and analysis, and how we achieve all these aspects in practical situation like in a plant environment, how dependability is ensured. Those things also we will discuss. Now, dependability, what is the definition? Again, same, this reliability, availability, maintainability, and then wherever we feel like durability is one of the alternative to reliability that is used, and safety and security as I mentioned. So this is the basic of accepted or more common definition of dependability, and we'll see that in the following slides the dependability framework, so it will be more clear. Okay, so in RCOM the dependability has been adopted. That means the core principle remained same, but the approach to implement them or to assess them, evaluate them has been slightly changed. For example, reliability is a probabilistic aspect, but you know in the present, especially in R&D domain, and even to some extent in engineering domain also, this technology is entered. This is called prognostics and health management, which leads to remaining useful life estimation. That means we have moved from a concept of probability of failure, wherein the epoch of or the instance of failure has not been given because that science was not available. But now with the prognostics and health management, where we are monitoring a component and trying to track the degradation, and that's why we are trying to get the RUL estimation. And the topic of safety itself, when we say it is an overriding factor, then probably we should have some scientific paradigm, that is risk, which is mathematical in parameter. So why not achieve and see for ourselves in a quantitative number how safety is improving and risk is reducing. So that is another, that's what the central idea in risk based engineering. Then in traditional dependability modeling, we are having a focus on all hardware components and things like that, but then we forgot that human is a common element, whether it is a design, operation, maintenance, reliability assessment, availability, everywhere human is in. So human factor and common cause failure, these two get a dimension in risk conscious operation management, and that is what has been proposed in risk based engineering, the core of this technology. Now at the end of the day, because I know I am talking to a community which are trying to focus on science and technology and trying to see for safety and security of systems and all, we will be crossing our academic limit to, we will go into how things can be pursued from R&D domain, because that is what we all want to be, scientists. So we'll try to see whether the metrics of risk can be an integrated parameter which can take care of all our attributes that we consider in dependability engineering. Okay. So what I was discussing in my previous slide, I'll discuss about where I was little you can say uncomfortable with the traditional approach to dependability. Availability and reliability, these are basically carrying a lot of probabilistic notion. If I have condition monitoring, then I'll know this component will not be available because I am monitoring through sensor. If I have RUL, then I know this component is going to fail or it's going to work for another couple of months or this thing, which is sufficient for me to manage safety and all that. Now safety itself is basically a qualitative term. Okay, safety improvement. If I do something, I say safety improvement, but how far? So we should have risk which should replace it. And then if we talk about confidentiality, integrity and maintainability, they are basically traditionally in their qualitative domain, wherein the probabilistic approach together with the new science, it brings it into more clarity and their application aspect are improved. Now how they are achieved? So fault prevention, how we'll do that idea, it comes from root cause analysis. Unless until we do root cause analysis for the failures, we will not be able to avoid the recurrence of this thing or eliminate this kind of failures. So fault tolerance systems, yes, we are building, but how they are effective, that will be known only when we do a quantitative analysis. Fault removal, that again will require knowledge of root cause analysis, fundamental causes of failure that led to the, it could be design fault, it could be operation fault, it could be maintenance fault. So we have to focus on those things. And what are the threats? Threats are nothing, fault, error and failures, which are nothing but they culminate into a risk. So if we look at it, okay, what is the more effective paradigm that we should develop, and that should be, so we have to deterministic. Yes, it has done very well for such a long time, and nuclear plant, if you say that they are the safest system and have maintaining the highest safety record, so this deterministic approach has been even in other process and industrial system also they have been used a lot. So let us talk about it. So defense in depth, protection and barriers, conservative approach. Now again, when I talk about conservative approach, now we have this probabilistic modeling and all that. So there uncertainty replaces and then it tries to throw, or rather it throws really in real time the kind of conservatism that is built on in a quantitative manner. So we have a better redundancy. Now we might say that one system is redundant to other system, but common cause, especially natural event, can knock off two redundant system also, or even internal event. So that we have to take into account. Diversity, one system should be in principle operation of should be independent or different even from the science fundamental science perspective. Fail safe criteria, single failure criteria, they are the basically tools and methods that have ensured quality control. Reliability came quite late, but before that it was a quality as a powerful instrument that has ensured all the branches of operation and maintenance and safety. Now when we have probabilistic approach, in probabilistic approach it is required it is required to have quality policy, because quality in PRA, quality in analysis, quality in reliability assessment, this is very important. So we have moved from quality assurance to hardware or procedures or methods to even the analysis methods also, and there are international documents that are available. So having that, then probabilistic risk assessment provides a very powerful technique to integrate the whole plant and provide a single statement of risk from the plant. And then we have their technology, reliability, availability, maintainability. These technology as well as the data, they go into building the PRA model of the plant. And the most important thing is here we don't see any human factor here. So what we try to say is here, whatever operations we do, all these things they have a human element. So human factor should form. So that's why risk conscious operation management, this term has come, and we have this system and operate. We can divide into two parts: safety system and process system. We know, we have discussed in previous lecture, and typically a complex system is characterized by control room operation and then distributed areas where operation maintenance are ensured and communication methods come to control room, and finally the final decisions are taken generally in control room, and then we have performance indicators. So these are this is the interpretation of dependability in risk conscious operation management, human factor, and so many quantitative criteria for decision making. Now the major elements of industry approach to achieve dependability, what we discussed was what in analytical domain, or but then how they are realized during normal industrial ecosystem. So by design, enhanced defense in defect, quality assurance, these are the organs of society or industrial ecosystem where we have to ensure, that is design should be, and operation should be defense in depth principle, conservatism, all this, and then quality assurance. Quality assurance in component, quality assurance in activities, and then independent agency like a regulatory agency overseeing the operation. And then normally for complex system it is 24/7 operation monitoring and surveillance is required, and then special efforts are made in human factor. Like in previous slide I had mentioned that human factor, so this is the place where training and qualification, where the human factor is entering. And then as far as the design is concerned, even traditional approaches, they used to have ergonomics, placement of equipments, which equipment should come. So but then there used to be a qualitative argument for arranging the control room, or even the site areas, site location, site layout, and the safety technical document for the plant. This is basically called technical document, which stipulates various condition and various factors that determine directly the safety of the plant. And while moving away from this tech spec requires a regulatory intervention. Even by chance, if we have done it, we have to propose, we have to get a clearance from regulator for those issues. So safety technical document is the most important document in the plant. There are other documents, emergency procedure, plant procedures, so many documents are there, daily logs and all that. But then this document is basically can be called a key safety document that is available in the plant. Engineering, design and domain specific scientific and technical support, maintenance management. So operation is not a thing, something operating in isolation. Maintenance is a part of, planning is a part of it. So that's how we say that the dependability aspects have been ensured. Okay, and then in service inspection because the condition of the passive component and rotating components, they should be seen what is their condition. So in service inspection, which is condition monitoring also, performance evaluation integrated way how the plant is performing. It is again a systematic study, and then what we have periodic safety evaluation by independent agency. So, and periodic safety assessment and review, provision for security assessment. So, as I mentioned in previous slide, now safety is one thing, but security also has taken over, and then now security aspect. So, safety is considered ensured when we have traditional random failure that contribute to safety or risk, and then security aspect they contribute to safety. So, these together they make the complete statement for safety, provision for security and all, and implementation of management safety culture. Safety culture is an important thing. So, you have seen whatever discussed in academic domain or in R&D domain, how they are implemented in real time scenario. So, this is called implementation of dependability through this method. There are many more. I have selected few one. Okay. So, now come to our approach, that is reliability is a probability of failure free operation. That is what we mean in simple words. If we take the proper definition of reliability, I will come to that in a new slide. Satisfactory operation in the sense that it should serve for the certain period of time that is determined and under certain conditions. Okay. So, availability, that means a component system should be available when it is required to perform its function, and sometimes it has got an operational concept also, wherein uptime, downtime they measure the availability. Maintainability is basically how effectively maintenance can be done to achieve the plant operational target. At the same time, ensuring safety of the plant. And probabilistic risk assessment, analytical model of the plant is created and to estimate the level of risk, and they are at various levels, and then one is ensured where we have to do modification, improvement, and where we are safe. So, you will find that you are rest assured that the plant has demonstrated its safety capability. And common cause failure is a very important thing I have seen. So, and of course, here we have not added the human factor which goes into, of course, integration of human factor into the last but one bullet we have over here. So, here we have in this lecture what we have discussed is dependability matrix, how it is interpreted in the real plant environment. Okay. So, this concept together they are called RAMs, but now security, durability, all those new terms have got added, and now in risk conscious operation management we take a risk based approach, because we feel if risk based approach, because even if the plant is so let us say reliability, now failure free operation. So, let us say plant has tripped, but then that trip has taken away some time which has reduced our availability. So, that is a fraction of time that is reduced. Now, plant has got maintenance problem. Now, maintenance also has taken up some availability. So, uptime, downtime, everything they comes, and directly or indirectly they form part of a PRA model. And then we saw the practical approach. Operation ecosystem also we have discussed, and with that I think we have come very close to understanding the risk conscious operation management and what we are talking about, what complexity that we are talking about, and identification and management of failure, particularly human factors and critical to dependability matrix. So, this is the overview of the lecture 1. We will move on to lecture 2 for the second week, and that will be reliability aspects.